Hi, I'm Robert Hryniewicz, and this is a quick recap of our meetup on the self-driving car. I begin by talking about my experience with my team, Team Case. We used this vehicle for the 2007 DARPA Urban Challenge competition. I begin by describing an array of sensors that we've mounted on this vehicle, from LiDARs or the laser scanning sensors to radars, stereo cameras for depth perception, and of course GPS antennas. I moved on next to this vehicle, which is the small version of our DARPA Urban Challenge competition vehicle. And as you can see, we also have similar sensors such as a miniature version of a LiDAR sensor, a stereo camera for depth perception. We have the power supply for the NVIDIA Jetson TX2 card, which is the brain of the vehicle itself and was used for real-time prediction or inference of our deep learning models. This is the actual track that we used and the live demo during our keynote at the DataWorks Summit. As you can see, the car is trying to navigate and stay as closely as it can on the red lines. And basically, if the angle is off, it tries to adjust and go back to being on the center of the track. One thing to remember is in the real autonomous vehicles, there's going to be a lot of data that will be collected. One estimate goes as far as 4 terabytes of data per day. So there's a lot of data, and one of the things during the meetup that we discussed is you need to have a right platform to be able to collect all of this data at such a large scale. We've demoed the training workflow, and we talked about it, what actually happened. So the vehicle would collect about 30,000 images plus the steering angles, and we would run it on 5 servers with 6 GPU cards, Dockerized TensorFlow, use GPU pooling so that you could pool all the GPUs together to have them being seen as one resource. And of course, you have the Zup notebook for your notebook environment to write your code in. Of course, once the model is trained, you can deploy it back on the vehicle itself and use the NVIDIA Jetson card for real-time prediction of how the car should drive. Here's the quick demo. So this is the actual notebook that we use. You can see we've initialized our NVIDIA cards, the P100s, and then we go over the different libraries that you would have to import, such as Keras and of course TensorFlow, Matplotlib for visualizations, and a few others. And first we will begin by the actual visualization. So this is the image that would be collected. This is a sample image, and what we have is the images with the steering angles attached. And I'll go into that a little bit later. So the actual files will be in a JPEG image with the steering angle and the corresponding speed. As we moved on, this is the actual model training that would happen. Let me start this, and I'll briefly describe. We have several layers in our neural net, from the convolution layers to max pooling, activation, flattening, and of course dropout, with a total of 3.6 million parameters. Let me pause this because it will take quite some time. Finally, you deploy the model, and then there's the piece where you do model debugging. So again, if you look at this image, then you could see what the actual activation map would be. The one to the left, you can see this is what we would really like is the highlighted lane that the car could focus on. And this is the lane, the red lane that the car would calculate the offset and then adjust the steering angle accordingly to stay dead center. And then of course we discussed the overall platform of the HTTP 3.0 and focus on the TensorFlow, the Dockerized version of the TensorFlow running as a Yarn container. Another piece that's very important is of course showing off how you could use Onbari to monitor and make sure that all the resources are available and monitor them as the training goes on. Here's the training plus the simulation itself. So in combination of the simulation and the real-time aggregation and collection of images with their steering angles would go through the flow. And this is a very simplified overview, high-level view. Once you actually train a program, you would have the trained model that you could then deploy again onto the vehicle itself. So the hardware architecture, a high level of generally what happens, and this is something that was reference architecture for us. Of course you have the steering and the wing angle via the CAN bus. You have some external solid state drive for actually collecting all the data, and then of course If you have multiple cameras, you could collect all these images too, from the left camera, center camera, and of course right camera. And similarly, the software architecture, once you have all the recording wheel angles, you would adjust for the shift and rotation, and then of course again you would pull all the images from these 3 different cameras, and then put it all into the convolutional neural net, or CNN. And then once you have the arrows, you would have the backpropagation for the weight adjustment until the network is trained with acceptable accuracy. So should you invest in a race car to train a model? Well, there's actually no need. You can still do all the training without the MIT race car, the race car that we've based our car on. And you could use Udacity self-driving car simulator. So here's an actual simulation to show that we've done for when we're training our vehicle. We started by having this vehicle drive on the center of the road. Of course, you want to specify where you're going to collect the images, and then once you start driving, you want to keep it as center on the lanes themselves, which is similar to what we have then done with the actual physical car. What you see in the left top side is the actual angle that the vehicle perceives and adjusts for as you make the turns, and these are the images plus the steering angles that then are used for training the actual model. So here's a 5-step of how to actually build and then train, and what the process is with the self-driving simulator. Of course, one is set up the environment with Unity. Next is you want to generate the data, and here's how the data actually looks like. Then you write the training script. On the right, you see a simple neural architecture that you could use with all the different parameters, especially the important ones are the convolutional feature maps. And then at the end, of course, you can see what happens is you have, again, the fully connected layer, and that what goes into the output vehicle. Then, of course, you train, and the process, of course, could take hours or days, depending on what's your hardware, CPU, and, of course, importantly, the GPU. And once you actually have the trained algorithm, you want to have a testing script. And more information, of course, is available on this trained model and references on the Udacity's GitHub. So definitely check these out. Next, of course, we discuss of what it takes to have a machine learning hat, and what are some of the problems that machine learning specialists actually deal with, and what are some of the problems. You can have recommendation systems. You could deal with fraud detection, natural language processing, or perhaps you're designing a personal assistant or doing some financial forecasting. And what do we use, and what are some of the libraries that we use? I think, of course, very popular are the scikit-learns, the XGBoost, the Spark MLlib, and of course TensorFlow, PyTorch, or Apache MXNet. So how do you do it? Well, first you start asking yourself, where is the training and test data set, and do you have access to it? It could be on HDFS, S3. How are you going to share it? Share it between the team members. Do you have distributed are you doing some distributed pre-processing with either MapReduce or Spark? And how do you do your experiments? Do you sample from the full data set? And how do you choose the state-of-the-art models? How do you tune the hyperparameters with cross-validation? And then, of course, you can have single nodes with CPU, single nodes with GPUs. But of course, you could train with the best parameters on a full data set, and that's a multi-node with both CPUs and GPUs, and that's where the yarn services really come in handy. Finally, of course, you got to push the model into serving, so you actually serve the model, so it's actually useful. So if you have the infrastructure hat, there are some different problems that you got to deal with. Of course, when a machine learning engineer sees generally is just the tip of the iceberg, versus what the infrastructure engineer sees are all the other components that are very important to actually support the training of these machine learning models. So what's important for this infrastructure machine learning engineer and how to make their life easier? Packaging everything, so making sure that all the dependencies are one. You have a GPU isolation, so that you can actually use these GPUs and not have them preempted with other services while you're doing your training. You want to have easier shared files, file systems, so you have access by the different team members, and of course tracking jobs and easy deployment. So you could do all these machine learning experiments on Yarn, just pack your dependencies in a Docker image and you can launch it. Here's what you need. You pack your dependencies, specify the resources and GPU resources in the Yarn service spec file, and launch the notebooks on the Yarn itself. So once you have the training code ready, you can deploy and train tasks on Yarn, and then, of course, depending on your schedule, you can run it daily, weekly, and so forth. Here's the spec file, and if you want to learn more, here's the end-to-end tutorial that we've posted on GitHub for either distributed or standalone training with TensorFlow. So some of the recent works on Yarn to support machine learning workloads like TensorFlow, again, importantly, is GPU isolation and scheduling support and native services. So it's easy to define and run any custom service. And all of that, of course, is available in Hadoop 3.1 under HTTP 3.0. So why do you need isolation? Well, you could have multiple processes that use single GPU, and they will be serialized and could cause out-of-memory errors. So with GPU isolation on Yarn, you get a granularity per GPU device. And of course, use the C groups and Dockers to enforce the isolation itself. So here's a quick overview. What happens, and of course, again, the Yarn supports the Docker as well as the NVIDIA Dockers plugin. So all of that combined gives you the environment framework where you can quickly train your models and use the best resources. So again, Yarn is great. If you've been using Yarn for scheduling and resource management, whether it's Spark, has Spark and Docker, Hive of LAP, big processing on all these 128 gigabyte nodes, and of course now with GPUs and Hadoop 3.1, now you can add other services. Here, what we talked about was TensorFlow on Docker, and of course you can add additionally Cafe and MXNet. So that's the recap. I hope you enjoyed. Definitely check out the meetup itself. It has all the details and more granular information. I will just cut it very quickly, and I'll definitely see you next time.